So, we will move on to a new topic and a new problem now. This is about a geometric data structure that I like to discuss with you. Actually, I want to cover two data structures. So, let us see how much we can able to finish, but we are not in a hurry. If you have any question, if something is not clear, please raise your hand. I will try to clarify your doubt. Okay. So, a typical geometric query is usually of the form that you are given a set of points, say in two-dimensional plane, and they say represent the age of the employees, each point represent an employee, and suppose the y coordinate of the point represent the age and x coordinate represent the salary. And the objective is to pre-process the input data, so that when a query rectangle comes, what is a query rectangle? In this context, the query rectangle is something like, give me the record of all employees whose salary is between say 2000, 20,000, 30,000 and age is between 30 and 40. This is a typical range query, and where we can find the application of this kind of queries? Have you seen this kind of queries before? The range is between this and this for multiple ranges. So, I can ask the same question in a d-dimensional space as well. Flipkart, very good. Yeah. And more specifically, databases. Databases, right? This is like a typical exam query that you have to, particularly in a certain range, you have to pick up the data from the database. There are many other such examples other than databases where this kind of queries are necessary, but not necessarily in R2, maybe in higher dimension. So, in both the data structures that I am going to describe works in d-dimensional spaces as well. But for the purpose of this class, we will only describe the data structure for the two-dimensional spaces. What is the naive way to solve this problem? How much time it will take? Query time. So, again there are three aspects. One is build time, how much time it will take to build the data structure, how much time insert and delete, how much time query. If I do not want to do any pre-processing, then how much time it will take? Order n time. I will just store the points. Whenever a query rectangle comes, I check with each point that whether it is inside or outside. So, with order n storage space, we can guarantee a order n query time. Of course, the question is, can we offer something which is sublinear, which is strictly a function which is strictly less than n? Do not want to spend order n time, can we do better? So, again when we see a problem in R2, what we do? We try to simplify the problem and try to consider it in R1. What is the range queries? Will be here, we have given a set of points in a line and we want to find out, given a range, we want to find out number of queries inside this. So, what we typically want to achieve is log n plus k. how to achieve here? We have a correct suggestion from here. What he suggests is that what we are given? We are given a set of points P1 to Pn and a range x comma y. Look for the lower value x in the sorted order of points. So, I can keep the sorted order of points and look for this particular element in the sorted order of in the sorted sequence. Suppose I find that the range is here. What I will do? I will keep reporting the points till I reach the point y, the sorted sequence, right. So, binary search, how much time it will take to find out where this, if we have a sorted line, log n time. But again there is a problem to the structure. What is that problem? Sorted I will spend n log n time in the initially, not an issue. What is the problem? Insert and delete. How much time it will take to insert or delete in a sorted array. So, these query points may change. Sometimes they will insert it, sometimes they will be deleted. If I store them in array in a sorted sequence, how much time? We have discussed this, order n. To insert a element in a sorted array, so that the resulting array would be sorted as well, this will take order n time in the worst case. If I use linked list, not going to help us. What we should do? Balanced binary search tree. But here we create the balanced binary search tree in a different manner. How? The same as the way we have created the segment trees. So, suppose these are our given set of points, we store them as the leaf node. In the balanced binary search tree. These are the leaf nodes. Then I will merge these leaf nodes one by one. How I am merging? Any node contains the maximum value of its left subtree. What is the maximum value in the left subtree? $28, right? And this can be, you have to again believe me that this can be done in order log n time. The maximum value can be found in log n time. So, I am creating the balanced binary search tree in a bottom up manner. So, what is the maximum here? 55. So, we have 55 here. Why I am pushing the maximum of the left subtree? So that it remains a binary search tree. So, this 40 is the maximum among all the elements here. So, all the elements are less than this, and all the elements here are greater than 40. If I have to find the element now, so this is how I am storing the integer values. If my input size is n, what is the size of the tree? because I am not storing every element in a one place. There are multiple places every element is being stored. For example, 40 is stored here, 40 is stored here, 36 here, 36 here. 2n, right? Anyone? No doubt that the size of this tree is at most 2n? Complete binary tree with n leaf nodes. How many nodes altogether they have? If you have a complete binary tree, homework. This is order n. So 2n we have 2n minus 1. Yeah, correct. So this is a balanced binary search tree. That means, well, let's forget about this. Assume that this is completely balanced. So total storage is order 2n. Okay. But the question is how to search for a query in this tree. Suppose now there is a query interval comes and I have to report all the elements which are inside the query rectangle. How to do that? Okay, but how I will traverse from 40 to 50? Too much time. So let us see. What I will do, I will first start traversing from the root and look for a split node. What is a split node is? A node whose value is inside this query range. Here in this example, what is the split node? If I traverse from the root, 40 is the split node. So one path goes in this direction, the other path goes in this direction. So 34 goes here and 80 goes here. So 34 reaches 28. Which path I should take? Right. I reach 36. I take left. But while I take a left, when searching for 34, there is a number sitting here. Can we say that this number has to be in the range? Whatever there, if there is a subtree here, whenever we take a left turn, the whole subtree has to be reported. Because I know that every value here in this part is between 36 and 40, and 40 is a split node. What does it mean? My right side bound is above 40 and I am taking a left path from 36, that my left bound is below 36. So whatever is there in this part of the tree, I have to report it completely. This is completely inside the query range. Looking for the left endpoint, looking for the path, tracing the path of the left endpoint. Whenever there is a right, whenever I have to move left, report everything in the right. So, I will go to 34 and again I go here, I report 36 here, I do the same thing for 80. For 80 what I will do? Go to 65, 70, I am going right. This whole subtree is inside my query range by the same logic. Doubts? Doubts? So, this whole subtree is inside my query range. Why? I know that everything is between 40 and 65, and this is a split node. My range is left endpoint is less than 40, and as I am moving on the right direction, my upper end is greater than 65. Hence, I should report everything here present in this subtree. This should be very clear to everyone. This is the building block for both the data structure in 2D. Clear? Raise your hand if this is not clear. Very nice. So, what I am doing here? I am, depending on my traversal, I am giving a color to each of the vertices of the tree. I am not actually giving color, because this will help me to explain. This is a hypothetical coloring. What are the white nodes? The nodes which I do not traverse at all. When I am looking for 34, I took this path. So, I never went to the vertex 10, 5, 22. So, this remains white. There are few vertices which I am visiting, but I am not reporting whatever is inside them. For example, 36, I am visiting, but I am not completely reporting this. I do not know at this point that whether I have to completely report these points or not. There are some subtrees which I am reporting completely, for example this. But here I am going on this path, but I may or may not report everything inside this subtree or not. I do not know at this point. When I am traversing this vertex, I do not know whether I have to report it or not. Right? For example, I am not reporting 90. What are the leaf nodes below 65? It includes 90 as well, but I am not reporting 90. So, I am not sure whether to report everything or not. So, I am making them grey, and the vertices which I completely report, the subtree beneath them I completely report, I am making them black. Why I am doing this coloring? It will be clear in a moment. So, similarly, I have another example. Find a split node. Does 40 is a split node for this query? No. So, what side the query is? It is greater than 40. The minimum range is greater than 40. So, I will move right. Does 65 is a split node? I split the queries and do the same thing. For future reference, this is the query and how to build. So, again the biggest question is how much time I am spending doing this. How many grey nodes can be there? How many white nodes? Do I care about white nodes? Not traversing. We are not even traversing the white nodes. I do not care. What about black nodes? Do I care about black nodes? No, because I will charge them on the output size. I want a complexity log n plus k while reporting all the points. So, I will charge them on the k part. If I just want to report the number of queries, what I will do? While building the tree, I will store a value how many leaf nodes are below this node. I will not go inside, I will just add plus 4 here. By returning back, I will return. So, I will not pay any complexity here for number of nodes if I want to. If I have to report exactly the nodes, that is on the output side. What about number of grey nodes? Twice log n. It is basically the search path of 34 and the search path of 80. Each search path have at most log n many values. Yes. So, what is the height of this tree? No. If I have n leaf nodes, height is log of n, order, everything is in order. So, order log n. So, each path is of size log n, order log n. Okay, because the size of the tree is order n, so size of the path is, length of the path is order log n, so everything is done by 2 log n times order log n, we are happy. And here we can insert or delete elements in log n time as well. Clear? One dimensional query. Doubts? So, this is the time we are spending for each query. Clear? Good. Questions? If this is not clear, we will be in trouble understanding the other things. Okay. How many white nodes we visit? 0. How many grey nodes? Log n. Grey nodes are the nodes which are in the search path of 34 and the search path of 80. It is a balanced binary search tree. So, from root to each leaf node is of distance at most log n. So, 2 log n grey nodes. What about black nodes? I do not care because I am reporting the black nodes, that is on k. Yes, of course.
So, there is no difference than an array.
No, we can add, delete.
It will get distorted and
There are ways to, by rotating by small or constant many rotation, you can maintain this balanced binary search tree. This is possible.
why don't you just store it normal base divided into copying the nodes? You could have just taken normal base tree with no copy.
We will see. We will see. So, one thing is that it is easier to understand. We will see, because this is not our final goal. Similar kind of tree. Yes. Yes, this is also n log n. To build this tree, it will take n log n time. So, everything is same, but this is just I am creating the tree in a different fashion. We will see why I am doing this for the storing the points more than once. Complexity wise it does not harm me to store. Let us see, this is not my final goal. Is it clear? One dimensional lens query to everyone? Raise your hand if it is, there is some doubts. Okay. This is for the range counting queries where the k part is gone because I will store them in the node, so I just sum it up. So, now we reached in 2-dimensional plane, and we would like to generalize this idea into a 2-dimensional plane, same idea. How we are generalizing? Let us see by an example. What we are doing, we are splitting the input into two parts by a vertical line first, which is a median vertical line. It divides the input into size n by 2 and n by 2. So, this line, I am finding this line. How much time it will take to find such a line? Order 1. How much? How much time it will, if I give you n numbers, how much time it takes to find the median? Order n. So, this is a median line. Median line is a line which divides the point set into exactly equal same part, almost equals parts. What I am doing, I am finding this line and divide it into data into two parts. I have two data set, one on the left, one on the right. For the left, I will find again a median line, but which is parallel to x axis, not parallel to y axis. This is the median line. That will split the data once again. Is it okay? How I am doing it? On the right hand side, I find the median line, divide it into equal parts. I will continue doing this till I reach a point where each box contains at most one point. Is it clear? Is it clear? Each stage we are dividing into half. So, this is actually a balanced binary search tree. It is log n. It's just dividing the half and half. Can be difference, can be at most 1. Because if there are even number of points, then 1 will be more in one side. Clear? So, what each internal node signifies in this tree? What does L1 signifies? This root node signifies. Signifies the whole rectangle. What does L2 signifies? L2 signifies this rectangle, right? In some sense it represents the points in it, but we can think of it, it represents as the whole rectangle. What are the leaf node signifies? the finer set of rectangles. These are the rectangles which you can see here are represented by the leaf nodes. This is the rectangles in this level. This is the rectangles in the previous level. This is the, if I delete this line, this is the first rectangle. This is all these nodes. And we have finer, this is this set of nodes. Then at the last we have this. Is it clear? Each internal node represents a rectangle as well as the leaf nodes also represent a rectangle. Is it clear? Raise your hand if it is not clear. Yes, sir. Where is P2? This is P2, right? Why this is? L1, right? Yes. Here is the P2. This is L8. Oh, P2 is not in L8. PT is not in L8. Yeah, P2 is in L8. So I am assuming this is a median line, I am putting it considering this here. So if you have a situation like this, then the median line will go through this point, then you have to consider either this here or this here. I am considering this here. Now L2 divides it into two parts, P1 and P2. L8 divides it into two parts, so L8 divides into P1 and P2. One side is P1, one side is P2. But having said so, there can be multiple errors in the drawing. So pardon my drawing. It may be, there may be present, there might be multiple errors. But the idea is clear to everyone what I am doing here? Good. This is the algorithm. Of course, I will not go through the algorithm, but this is fairly straightforward. This is the thing that I have said, that is what we are doing here. Complexity? I should. What is the complexity of this algorithm? To build. How much time will spend to build? Simple recurrence, right? Tn equals to median line. How much time it will take to find the median value? Order n. A complicated algorithm, but we can find median in order n time. Then I will call build left subtree, build right subtree, that is recurrence, two call recursive calls of size exactly n by 2. You solve this recurrence, you get this. It's a very standard recurrence in the world of computer science. So in n log n time we can build. The easy part is over. How to query? So try to think it like this. I will start with root. There is no split node. We will start with root. This is the blue one is our query box. Is it visible from the last? I will start with the root. We will check whether this is contained in the rectangle in root. Yes? Does it intersect the left rectangle and the right rectangle? Yes. So we need to search in both the directions. Right? So we go left and see that we have this line. does this rectangle, query rectangle represent in this side as well as in this side? No, it only represents below. So, I will only search in the left. I go to the left and I ultimately see it goes right and I report only P3. But it may so happen then this is a query rectangle Q. Q completely contains the rectangle associated with L3. Q completely contains the rectangle associated with L3. In that case, what I will do? I will report everything below L3. Suppose the rectangle is, the query rectangle is like this, right? So, what I will do? I will report everything here. What is the rectangle associated with L6? This is the rectangle. If my query rectangle is like this, then I have to report everything inside here. So, I will make this node a black node. So, depending on whether the query rectangle completely contains this or not, so there are three cases. Query rectangle does not intersect the rectangle at R3, let us call it R3. Query rectangle Q intersection Ri equals to null. In that case, what will be the color of this Ri? It is white. I will not search because it do not intersect the rectangle. The query rectangle do not intersect the rectangle represented here. If it intersects, but and Ri is a subset of Q, then report everything inside. Are you with me? If the query rectangle contains a rectangle fully which is represented, then I have to report everything inside. So, I will make that vertex black. If it partially intersects, I will make it grey. Clear? The same thing that we are doing previously. If the interval is completely inside the query interval, make it black. If it intersecting, we are making it grey. If it is outside, we are making it, calling it white. Doing the same thing. Okay. So, take a good example. This is the query rectangle. What we are looking for? We have to report all the points present inside the blue rectangle. The query rectangles comes on the go. We have to report according to that. So, does this suppose my query rectangle is a red rectangle. So, what is the rectangle stored at L1? Is a full rectangle? Does it intersect the query rectangle? Yes. Does the query rectangle contain the rectangle which is stored at this point, which is represented at this point? No. Do not, this red rectangle do not encloses the blue rectangle, right? So, does it intersect the left and the right? Yes. So, you have to search in both the parts. Let us concentrate on the right. Right is what? We have this rectangle. This is the rectangle which is stored at L3. Call it R3. Does R3 intersect with query rectangle Q? Query rectangle is a red one. Yes. So, it is not white. Does R3 is contained in the query rectangle? No. Does it goes to left and right? Yes. So, I have to search in both the direction. Let us come this side. So, what is the rectangle represented by L6? Right, this is the line. This is the line which splits from here. Now, look at this rectangle. Does this rectangle, does query rectangle contains this whole rectangle? So, what is R9? R9 is a purple rectangle. Does the red rectangle contains the purple rectangle? So, this for this query, this vertex will become black. Why? We have to report everything inside because it is completely contained in the query rectangle, and all the vertices below this will become black. But this is grey because it is not completely contained. The same thing that we are doing for the 1D case. Now, is it clear? It is a simple strategy. We are doing these three things, just marking, but do not think about the query complexity right now. Is the scheme clear? I know that each vertex contains a rectangle Ri, each Vi is represented by a rectangle Ri. I am just checking whether what is the relationship with Ri with this query rectangle Q. Depending on that, I am giving it some colors. Okay. Are you with me still? Please raise your hand if it is not clear. My bad. Because I have not checked after creating this. It should be should be L10. Thank you. I will make the change the mistake. But is the idea clear to you? Okay. It is a mistake. Sorry. Good observation. Yeah. Here is one culprit. Here is another one. Sorry. Is the idea clear? Straightforward. Quite straightforward. Now, let us think about the query complexity. How many white vertices? 0. We never traverse the white vertices. So, 0. How many black? I do not care. I will put it on the output size k. Only thing is, I have to count how many grey vertices. What do you think? Is it clear that we should only concentrate on counting the grey nodes per query? Let us see. This is a general scheme. This we are doing for a long time. This is our point of interest. So, this is or balanced binary search tree. And what are the small rectangles represent? The leaf nodes. My question is, among these leaf nodes, how many gray nodes can be there? Forget about the other part of the tree. Among the leaf nodes, how many gray rectangles can be there? Okay. Property. When a rectangle is gray? When it is partially inside the query rectangle. That means a rectangle is gray if and only if among these 4 lines at least one line stabs them. So, this is gray, this is gray, this is gray, this is gray. This is black, this is completely inside, in the lowest level. Forget about 4 lines. What I have a grid-like structure. How many rectangles? N. When we stop, there is one point in the, each rectangle contains one point. So, this is a root n cross root n grid. There are n rectangles altogether. So, in some sense this is a root n cross root n grid. If I give you a horizontal or a vertical line, how many rectangles you will be able to stab here? Rectangles you will be stabbed. The stab means this is a stabbing. So, we stab 1, 2, 3, 4 here. One line, root n, right? You will be able to stab root n many lines. Still with me? So, in the lowest level, you will be able to stab root n. Here, how many vertices are there? N by 2. How many rectangles are there? N by 2. How many you will be able to stab? Root over of n by 2. This is root is like full. If I sum this, magic. This is order root n. Again, yes, because how I am dividing into 2 parts, always exactly same number of points are in both the sides. Stopping when there is one point inside the rectangle. I stop.
Each number represents the rectangle.
What?
If there are n points,
Yes.
one represents one rectangle, second represents second.
In the lowest level, yes. In the finer grid, the rectangles we have represent the leaf nodes. So, think about this once again. Think about one horizontal, one vertical line. How many rectangles I can partially cross? I can partially cut. How many rectangles? This is root n. Number of nodes here is n by 2. So, root n by 2. So, if I continue doing this, I will get something like this, and you sum up, it is order root n. We have done it for one line, for 4 lines, 4 into this number. Yes. Find out the number of points inside the query rectangle, or the points inside the query rectangle. Yes.
By gray rectangles like that,
Yes.
you mean that that intersects, that the final rectangle intersects the query line.
Yes.
But it may happen that the point is actually outside the query line.
Yes. I'll check. That's why I'm going inside.
So
In this L3 is gray with respect to this. I'm not saying I'll report everything inside. I don't know. So I have to go inside. That's what I'm saying. But when I'll go inside L3, what is L3?
so in L4, consider L4 now.
L4 here. Yeah.
So whatever we
So what is L4 here? This. What is the query rectangle, the blue one? Does it intersect L4?
yes.
So that's why it's gray. It intersects, but it does not contain.
That's fine. Left side we are ignoring because it is not inside. Right side again it is,
Yes?
but P3 is outside the rectangle.
Yes. So I'm not saying that I will report everything. That's why if I have to report everything inside gray rectangle, I'll put it on the output on K. So there are three. What I'm doing here? Black nodes, I'm charging into the output K. White nodes, I don't care, I'm never visiting. Gray nodes, I don't know how many gray nodes I have visited. Because gray is a dicey case because inside gray I may report or may not report the points. So I cannot directly say that, it depends on the output size. So I have to actually count how many gray nodes I am visiting.
What will that be?
That's what I am doing here.
No, what will that count be? That is
Root n.
number of points.
No, that will be root n. How many gray nodes? So clear your views. Is this clear? Black nodes, white nodes settled. How many gray nodes? That we want to find out, right? Is it clear? When a node, why this node is gray node? Say. Because the rectangle represented by node, this node, intersects the query rectangle. So in other words, among all the nodes stored here, among all the rectangles which corresponding to these nodes, I am looking for the maximum number of rectangles that a query rectangle can intersect, properly intersect, right? How many rectangles in the lowest level of the intervals, in the leaf nodes, this query rectangle can intersect? In the lowest level, this is your rectangles. In the lowest level, this is your one rectangle, this is your another rectangle, this is your another rectangle, maybe this is R1 is here, I don't know, maybe R2 is here. This is a finer division of the plane. I have to find out these fold lines, how many rectangles this fold line can stab. I want to find out how many rectangles a single line can stab. I will multiply it with 4. Right? How many rectangles among this set of rectangles a single line can stab? Root n. So in this level, I am spending root n time. If I go one step earlier, see this is the finer set of rectangles, look at the figure. Now one level, what are the rectangles? One level up, what are the rectangles? These are the rectangles. This was the previously, this is a new. Among them, what is the size number of these rectangles? N by 2. How many one line can stab? Root over n by 2. So if I take the summation, so here root over n by 4, root over n by 8. This is order root n. So number of gray nodes I will visit is at most root over n. So what is the total query time? This is white node 0, root n plus k for the black nodes. This is the query time for this data structure. Root n many gray nodes, k many black nodes. K is on the output side. Because I know k is completely contained, so I will report everything inside, I don't care.
Complexity I understand.
Hmm.
It is intersecting with the
We are not reporting the rectangle. We are reporting all the points. So you see that what is this node?
no, at the end I'm saying, at the end, but at the single
Yes, I'll reach here. Suppose there is still gray.
yes, that is great.
Gray, I have a rectangle Q. There is a point P here. I'll check whether the P is inside. I'll report. If the P is outside, I'll not report.
That is the part.
Yeah. Okay. Yes.
Previous level, how it become the whole root of n by 2? Isn't it root n by 2?
Nope. If there are k nodes, how many lines it will stab? How many boxes I'll stab? If there are k boxes, root k. How many boxes are? How many rectangles are here? N by 2. So how many boxes you will stab? Question? Not difficult, just a bit of tricky. Any doubts? So at n log n storage, we are able to reach a query complexity of root n. But there are techniques in computational geometry by which you can do it in log n time, where the storage will become, the pre-processing time and storage time is n log square n, but the query time becomes log n. Okay, so I don't think that I will not go into the details of that. I bugged you enough. So I will stop here.